Okay.
And I'll share my screen, which is the notes that I've sent you. Hang on a sec. Righto, can you see those?
Yeah. Yeah.
Okay, I don't know whether you probably haven't had a chance to look at it with Easter in between, but we're going to talk about ventilation. This is another pretty big topic, but you probably touched on it a bit already. So some abbreviations: natural ventilation, commonly called NV; mechanical ventilation, MV; car park exhaust and supply. I bring up car park exhaust and supply because that's a special case of ventilation. And Philip and Ivan wanted me to cover this first with you. So we'll talk about ventilation in general, car park ventilation today, and then I've got a little exercise for you to have a crack at, see how you go, and we'll talk about that some more probably next week, and other ventilation next week as well. So a space used by occupants within a building must be provided with adequate ventilation consistent with its function or use in order to provide health and amenity. So we all understand ventilation. You need outside air for breathing. You need to extract stale air, or so ventilation of normally unoccupied spaces may also be required for several reasons, including removal of odours. So let's say a bathroom exhaust, toilet exhaust, removal of heat, maybe a switch room or a plant room, which gets hot with equipment, machinery, gets hot. You need to keep it under a reasonable temperature. Removal of moisture, again, could be a bathroom, taking the moisture out. And removal of dust or fumes, they're just a few examples. Outside air is normally supplied to a building through the air conditioning system or through supply air fans and ductwork. And exhaust air is removed from the building with ductwork or fans. So I'm just going to introduce you to the relevant codes, which I try to do each time so that you're familiar with what applies to ventilation. The NCC, National Construction Code, which sort of factors in most things that we do. Volume 1, Part F6D6, ventilation of rooms, states the following: a habitable room, in other words, a room that people occupy, office, shop, factory, workroom, sanitary compartment, bathroom, shower. This is verbatim, straight out of the code. Laundry and any other room occupied by a person for any purpose must have either natural ventilation, complying with F6D7 and AS 1668 Part 4. NCC doesn't actually say AS 1668 Part 4, but it's the Natural Ventilation Code. Or it must have a mechanical ventilation or air conditioning system complying with AS 1668 Part 2 and AS/NZS 3666 Part 1. AS 1668 Part 2 is the main code that you need to really get familiar with, because it'll be the one you use the most in your work. And I'm sure that you've already touched on it, or we've talked about it, but we're going to go over it again and again for different parts that apply to what we do. So I'll just have a quick look at the NCC. So this is Part F6D6, ventilation of rooms, the bit that I just read out at the start there. Talks about natural ventilation. Now, natural ventilation applies to most buildings, but or it can be used on most buildings, but it's sometimes difficult to apply. But the area that we probably use the most for natural ventilation would be bathrooms, provided you've got, if you're doing a, say, residential apartment, you can naturally ventilate the apartment normally because it'll have windows to the outside, doors onto balconies, things like that. So you can, most apartments will be naturally ventilated. So the key is there must be a ventilating area not less than 5% of the floor area of the room required. So you can use windows, doors, any other openings, and open to a suitably sized court or space open to the sky and so on. So that's something to be aware of. We would use natural ventilation where we can, because obviously it's cheap. The builder is going to provide windows and doors and so on. So if we don't have to provide mechanical ventilation, we don't do that. It doesn't often apply to a commercial building because you can't have open windows and doors. So you have to have mechanical ventilation. So while we're on the NCC, F6D11 states requirements for car park ventilation and makes reference to AS 1668 Part 2 for mechanical ventilation, or AS 1668 Part 4 for natural ventilation. There are some requirements for car park ventilation systems as well, specified in AS 1668 Part 1, which is the fire precaution code. You probably haven't had much to do with that one yet, but or have you? Part 1? Okay, well that's another important code. So 1668 Part 1 and 2 will be the most used Australian standards that you'll come across in this work. And NCC F6D12 states requirements for kitchen local exhaust ventilation. So using kitchen exhaust hoods, and makes reference to, again, 1668 Part 1 and 2. So if I just go back to the NCC, look, you can have a read through this in your own time, but I'm just mentioning these because they're relevant to our discussion at the moment. So F6D11, every story of a car park except an open deck car park. So an open deck car park is like the top floor of a car park or something. You go to a shopping centre and you drive right up to the top. It's open to the sky, so that's naturally ventilated. You don't have to put anything, no mechanical ventilation, but floors below that may, if they're below ground, they'll certainly require mechanical ventilation. If they're above ground, they may or may not require mechanical ventilation, depending on a lot of geometric factors. But big car parks will normally require mechanical ventilation. So that's the car parks. And kitchen, I just mentioned that as well because we'll talk about that a lot more, and this will be something that you're going to be working on quite a bit. We may cover it a bit more next week. We'll see how we go, but there's a lot in kitchen exhaust ventilation as well. But this is talking about local exhaust ventilation, which is where you have a kitchen hood in a commercial kitchen, and it gives some requirements about when you have to do that. But generally speaking, a commercial kitchen, or even, a small, well, it's still commercial, like a fish and chip shop or something, will have a kitchen exhaust hood to take away those grease, vapours and smells. And that the wording in this clause of the NCC is identical to what you'll see in AS 1668 Part 2. It's just the exact same words. And then 1668 Part 2 goes into more detail about how you work out the size of a kitchen hood, the type of kitchen hood to use, the airflow rates, and other options. So moving on, the requirements for ventilation rates are set out for the majority of buildings in AS 1668 Part 2. Appendix A lists the requirements for outdoor airflow rates, and Appendix B lists the requirements for minimum exhaust airflow rates. So are you familiar with these?
No.
Okay, well, I'll show you. I've got that ready to go. So this is Appendix A. Now, bear in mind, there's a lot of text in the relevant sections that talk about this, but this gives you a summary. And when you start doing design, you'll go to these appendices quite a lot to look up whatever type of building you're working on. So the type of occupancy, net floor area per person is one option if you don't know how many people there are in the space. Or quantity is the outdoor air flow rate per person, and that's the unit. So for instance, a classroom serving children up to 16 years of age, 2 square metres per person if you don't know how many kids there are, and 12 litres a second per person is the outdoor air flow rate that you need to apply. Generally, classrooms, you probably allow up to 30 students at 12 litres a second per person. If they're over 16 years of age, it's 10 litres a second per person. Okay.
Why don't the kids get less? Get more.
The younger kids get more, I think, because they tend to run around more at lunchtime and things like that, and they get a bit hot and sweaty and smelly. So I think that's the simple background to it, that you need a little bit more for the younger ones. The older kids, you know, they go out and have lunch and come back in again. They don't do too much at lunchtime. Well, it depends. They might go and kick the footy around all lunchtime and come back hot and sweaty. So there's various categories there as we go down. General areas, healthcare. Just be a bit careful if you're looking at this healthcare one, because if you're doing a hospital or a medical centre, there are usually other codes that apply to those as well. Hotels, motels, resorts, etc., etc. Offices, and this will be one that you'll look at a lot. Conference rooms, office areas, waiting areas, and so on. So that's, you can see there, it's all 10 litres a second per person. But this gives you the square metres per person if you don't know what it is. But you're always better, if you've got an architectural drawing that has a plan of desks or layout of tables or whatever, and it sort of shows the seats, you're better off to use the actual number of people that are proposed, because it'll usually turn out to be less than what you would find if you used square metres per person. So you need to use your discretion a bit, because what we want to aim to do is reduce the outside air quantity as much as possible, because outside air brings with it heat. Okay, if it's summer, it's going to be cooling requirement. If it's winter, it's heating requirement. So we want to try and minimise that. Also, 10 litres a second per person can be reduced to 7.5 litres per second per person if you're using appropriate filtration. So we haven't talked about filters yet, but it was on my agenda, but I've changed that a bit. So probably in a couple of weeks' time, or 2 or 3 weeks' time, we'll talk about filters, and I'll talk more about this. There's a number of equations in AS 1668 Part 2 that allow you to reduce the outside air depending on the filtration, depending on the dilution with return air, and other things. So that's another big topic. We won't go into that now because we will run out of time. So moving on to Appendix B, this is the minimum mechanical exhaust air requirements based on the use of the enclosure. So automotive vehicles, see Section 4. We're going to talk about that this morning. Change rooms, 5 litres a second per square metre of floor area, etc., etc. There's healthcare there as well. Again, just be careful using those numbers, because there might be a hospital code or something else that overrules this. Kitchen areas. This is on top of the localised hood, 5 square metres per litres a second per square metre. Now, we'll just quickly have a look at this one. A sanitary compartment. So this is a bathroom or a toilet. The figure is, in those yellow highlighted ones, there are figures that MEPEC have chosen to use, which are above the standard requirements, because we feel that we need a bit more air than what the code says. But the minimum requirements is 10 litres a second per square metre of floor area, or 25 litres a second per listed fixture, which is a toilet or a urinal, or, you know, things like that, or a bath, shower. So that's for a commercial building. For a residential building, so an apartment, you can have 25 litres a second per room. So a bathroom, which has got, say, a shower, a toilet, or it might have a bath in it, it's just 25 litres a second for the room. And so on and so on. So we'll talk about that more in a later, probably next week. Now, I want to get on to car park ventilation. This is a big topic, and it's one that you're going to be asked to look at quite a bit. And I've added a couple of notes in. I'll send you these notes as well, so you don't need to write this down. I've just added these after I'd sent it to you. Clause 3.3 and 3.10 of AS 1668 Part 2 defines objectionable and non-objectionable exhaust air and discharge requirements. Now, this is important to know this, so I thought I'd bring it up now. It turns out the car park ventilation is not objectionable. So that's a good thing, because objectionable discharges bring in a whole lot of other requirements. But I'll just show you this quickly, and you can have a read of it when you have time. It's 31. Okay, local exhaust. So there's two types. There's type A and type B. Type A, significant localised sources of toxic, irritant, asphyxiant, offensive, and so on type exhausts. And there's a note down the bottom here, C331. Type A effluents are emitted by welding processes, chemical and microbiological reactions, degreasing tanks, and so on. Nasty, smelly, dusty sort of environments. Type B is basically kitchen exhaust. So we're talking about kitchen exhaust hoods. And again, this is what's quoted in the NCC that we looked at before. So car park exhaust and toilet exhaust are basically non-objectionable. I'll go down to 3.10. Right, now, there's a few other important things here which we can talk a bit more about next week. But these tables, it's worth having a look at these enclosures that may be served by a common exhaust system. Sometimes you might want to combine exhaust systems and say, oh, we've got an exhaust coming from this room and we've got a toilet exhaust coming from this room, and they're both going a long way and then out at the same point of the building. Can we join them together? Well, the answer is probably no. They have to be separate unless they fall into these categories. So group 1, for instance, airlocks, bathrooms, change rooms, laundries, locker rooms, privacy lock, anything to do with cleaning or bathrooms can be combined into one system. So if you've got a cleaner's storeroom, for instance, and a toilet exhaust next to it, they can be combined together. But you can't combine a toilet exhaust with an area where food and beverages are prepared or consumed, because you might get leakage from one to the other, particularly from the smelly zone to the occupant zone. So it makes sense, and this just defines what you can combine, and by using that, you can then say what you can't combine. And I have seen designs. We did a big hospital job, which was designed by consulting engineers, and they had combined a certain exhaust with another exhaust. And I looked at it and said, well, I don't really think you can do that. And under the code, you couldn't do it. And we had to split those exhaust systems, and it turned out to be a very large cost, a variation to the contractor, because to run another exhaust system, all the ductwork and fans and controls, turned out to be quite a lot. So be careful with that when you're doing designs, that you don't combine exhausts that you're not allowed to. Table 3.3, objectionable effluent discharges. So if you've got type A effluent, which I mentioned just before, that applies to any flow rate. So this is where you're discharging the exhaust from the building. Type B effluent, which is a kitchen exhaust hood basically, anything greater than 1,000 litres per second has to comply with the 331, oh, sorry. It's got to comply with 310.3, which is discharges deemed objectionable. I'm not going to go through this now, but just be aware of it. So anything that's not deemed objectionable has to comply with these. So the requirements for objectionable discharges are much more stringent than non-objectionable. And so going back to car park exhaust, the requirements for discharges are not too stringent. In other words, you can discharge at street level. You can discharge out into the street because the air you're discharging is basically the same or probably better than the air in the street anyway. So it's really about getting the objectionable discharges away from people. We'll go through that more later. But there's another table here, 3.4, which talks about the separation between discharges. And it's really talking about if you've got an outside air intake and a bathroom exhaust, how far apart they need to be. Back in the old days, it used to be 6 metres, no questions, that's it. But when the code's been updated, they've looked at it and said, well, we really don't need to have that bigger separation, particularly where you've got low flow rates, low outside air intakes. So it gives a list of less than 200 litres per second. It's 1 metre separation. So this just makes it easier for you to carry out design for small airflows. So then if you get up to 1,000 litres a second, then we're back to the 6 metre separation. So you'll find you're doing jobs where you've got, say on the roof of a building, you've got an outside air intake and you've got a toilet exhaust. How far apart do they need to be? This table tells you the minimum separation. Or if you've got an apartment where you've got a bathroom exhaust and an outside air intake, or let's say a bathroom exhaust and then you've got a window for natural ventilation. This tells you how far they have to be. So you're exhausting the bathroom out onto a balcony, but the balcony is also being used as natural ventilation for the living area. Does that make sense? Mm-hmm. Then the exhaust has to be 1 metre away from where that door opens. So that's important. You'll find you use that again and again. Okay, all right, we raved on enough. We'll get on to car park ventilation. Oh, excuse me, let me drink. So this is a huge topic, and I'm just going to sort of scratch the surface a bit today, and as we go on, we'll talk about it more and more. Car park ventilation, mechanical ventilation requirements are detailed in AS 1668, Part 2, Section 4. This applies generally to underground basement car parks and large above-ground car parks where the latter, the above-ground car parks, don't meet the requirements for natural ventilation. I'm not going to talk about natural ventilation of car parks at the moment because that's another topic again. The principal objective of car park mechanical ventilation is to maintain the carbon monoxide level below safe limits for human occupancy. So that's the key to all this, is getting the CO level down to where people can park their car, walk through the space, or hang around the space for a short time without being affected by car park carbon monoxide. Car park natural ventilation requirements are detailed in AS 1668 Part 4, and we will talk about that at a later time. As I said, car park exhaust air discharge is not considered objectionable. So it's not objectionable. That's important to remember, okay? So let's have a look at Section 4. 1668 Part 2, Section 4 provides a detailed description of the calculation procedure for mechanical ventilation of car parks. Generally, it comprises supply air and exhaust air systems, and airflow rates are calculated in accordance with clause 443 for small car parks, or 444, which is all car parks, including small car parks. But 443 just gives you a simple procedure for a small car park. 1668 Part 2 Clause 441 allows you to omit the mechanical supply under certain conditions. I'm not going to go through it at the moment. It tells you in the code what you can and can't do. So I'll just go to those. Okay, here's section 4, ventilation of enclosures used by vehicles with combustion engines. There's a flow chart there that tells you, ask questions and says where to go and what to do, but I'll skip over that and go down to part I'm talking about. 4.3 notation. There's a whole lot of symbols here and definitions of what they are, some of which we'll be looking at shortly. Number of car spaces. If you don't know the number of car spaces, then you can use this factor here to determine how many there are. But normally an architectural drawing will show you the car spaces and you can count them, or the drawings may actually tell you how many there are on the floor, so you don't need to count them all. So this is 441A. Mechanical supply may be omitted, provided each zone and level of the car park has openings directly to the outside. So in other words, if you've got enough, this would apply to an above ground car park. If you've got enough openings on the outside, you can possibly delete the supply system. Mechanical exhaust air system may be omitted, provided, etc., etc. So we're not going to go into that in detail at the moment, but there are possible exclusions there. Ventilation distribution. This tells you when you're doing your layouts where you need to put the outlets. We can't go through this in detail, but what I want you to do initially is to understand how the calculation is done for the amount of air required to ventilate the car park. And then there's an exercise for you to have a look at. So 443, simple procedure for small car parks with 40 or fewer car spaces. So you can, whichever one of these, A, B or C is the higher, is the one you have to use. You don't pick the lowest one and say, I'll use that. It's got to be the highest of these three. So N1 and P, N1 is the number of cars in the car park, which in this case is 40 or less, and P is the parking usage factor. There's a table here, 4.1, which tells you this factor depending on what the building is used for. And this is based on, obviously, the amount of traffic that they're expecting during a typical day. So a residential car park, people go to work in the morning or wherever they go in the morning, come back in the afternoon, and that's it. They leave the car there after that. Well, they may not even go out for a day or a few days or a week. Commercial car parks, you know, where you pay to use the car park, or it might be, well, yeah, basically where you go in, pay some money and stay for a bit of time. There's movement all the time during the day. So that's got a higher factor. Retail, food and drink services, again, higher. Entertainment and sports centres, higher again. Vehicle depots. So that makes sense. Or 2000 B, that means 2000 litres per second. So that's the minimum car park ventilation requirement. And for a small car park, 2000 may be the number that you use. It used to be 3000. They reduced it to 2. So that sort of made the systems a bit smaller. Or 2.5 times the area. A is the area of the car park. Now this is the effective area where cars can park and travel through the car park. If there are areas that are inside rooms, let's say there's a switch room or a garbage room or something in the car park, you don't need to include that area. It's just the open area to where cars can move through the car park and people can move through the car park. So 444, now this is the one that you're going to be using most often. Firstly, we need to calculate a contaminant generation rate. So C is the contaminant generation rate. And P again is this parking usage factor from table 4.1. N1 is the number of car parking spaces in the area under consideration. So if you've got a multi-level car park, it's N1 is the area that is the floor that you're looking at the time that you're doing that calculation for the contaminant generation rate. D1, we'll go back to the definitions. So D1 is the average driving distance in metres within the zone or level under consideration for the exit of a car parked there. So let's say you're looking at basement number 1. We'll go to N1. The number of parking spaces in the zone or level, that should be or level under consideration. Then D1 is the average driving distance within the zone or level under consideration for the exit of a car parked there. We'll talk about that a bit more in a second. N2 is the number of parking spaces situated in other parts of the car park having exit routes passing through the zone or level under consideration. So if you've got a multi-level basement car park, normally B1 would be the highest level of basement, and then B2, B3, B4, etc. as you go down. So let's say you're in B, you're looking at the exhaust you need for B1. Well, it's going to include the exhaust you need for B2 and B3. Well, sorry, the exhaust from that level is going to include the exhaust required for cars that come from lower levels, is what that's trying to say. Okay, so N2 is the number of parking spaces situated in other parts of the car park which have exit routes passing through the zone or level under consideration. So if we're considering B1, we need to consider B2 and B3 as well, because the cars have to travel up from B3 to B2 to B1, and then wherever they go from there, they'll go up to the ground floor and exit, most likely. Does that make sense? Yeah. So this contamination rate, that's what it's asking for you to do, to look at N1 plus N1 times D1 plus N2 times D2. So to work out D1, you can either sort of take an average distance that you think it's going to be for a car to exit that level, or you can use this in note 1, a distance equal to 1/2 of the perimeter of the car park in metres may be used as the value of D1 or D2. And if you want to see how C is derived, there's an equation in Appendix J, but we're not going to look at that now. So that's the calculation of C. And then we go to 4442, the airflow rate. So this is the actual exhaust rate. For car parks, the airflow rate in litres per second shall be calculated separately for each zone or level. So for each level, you're going to have to do this exercise, go back and calculate the contamination rate and look at the floors below it as well. So starting with B1, you're looking at, say, B2 and B3. Then B2, you're looking at B3 below it coming through. B3 is a floor on its own, and there's nothing below it. So I'll say that again. For car parks, the airflow rate in litres per second shall be calculated separately for each zone or level. We need to know that so that we can do the duct design for each level, and shall not be less than the greatest of A, B or C. So A is 0.85 times C, which you calculate for each level times E. Now E is given down here in table 4.3. So this gives you some parking options. So first option, no special parking procedure. So self-parking. If there's any staff in this car park area, they're in a separate enclosure ventilated in accordance with 422. So in other words, they have a parking box. You know, you've been into a car park where there's somebody standing in a box and collecting your money. You give them a ticket and you pay. Not so common these days, but you'll still come across that. So that's that situation. So that's got an E factor, staff exposure factor. This is again exposure to CO, potential CO contamination or poisoning. That's a factor of 1, which is the lowest factor. If you go up to no special procedure, so this one, for instance, sorry, try again. No special procedure, in other words, self-parking. You drive in, you park it yourself, but the staff are located in the enclosure. They're not protected from carbon monoxide. So that's a higher factor for E. And that, I think that makes sense. So you can look at all those different options depending on the car park. And then you multiply that by T. Now T is the vehicle type factor. So no special vehicle population. In other words, a mixture of petrol engines, diesel, electric is 1. Diesel vehicles, 2.4, quite high. LPG, CNG are both 1. Electric vehicles, 0.1. Now, you're not going to get a car park full of electric vehicles at the moment. Maybe in the future that might happen. And so on. So that you can do that calculation for A, and that'll give you a number for each floor. You have to do that for each floor, and you'll get an exhaust rate for each floor. Is that clear?
Yep.
Okay. Now the next one, B, 2000 times F times T. Now F is the staff usage factor. Again, you've got the parking procedure, and then over here it tells you what the relevant staff usage factor is. So you can work through and determine, let's say it's this one, no special parking procedure. You park the car yourself, and if there's an attendant, they're in a ventilated enclosure, so a factor of 1 for that. But depends on what it is, you'll get a different factor. And times T, the type factor again. So that's another one. So if it turns out that F and T are both 1, then that number is 2000. So again, that's your minimum exhaust rate, 2000 litres per second. It's probably not common that that'll be the answer, tell you now, but sometimes it is.
If that is the case, sorry, good question. If that is the case, F and T are 1, could you then consider it as a small car park?
Well, yes, possibly, yeah. But this is more of a general thing, so that will fall out. I mean, when you look at a small car park, if it's less than 40 cars, you'd probably go straight to that previous clause and use that, rather than even go through all this. Yeah. If you wanted to test it to see if it's actually correct, yes, you could do that. Right. So this clause 444 is for all car parks, but the other one just allows you to use a simple procedure if it's small. And again, you've got 2.5 times the area. In my experience, the ones that will dominate will be either A or C, and usually A, which means you've got to go through this process and do these calculations for each level and then add them all together. So that's basically what you have to do. I'll just quickly mention a couple of other things. So I've been through all that, what I've just talked about there. Clause 4.5 describes requirements for enclosures other than car parks. We won't go spend much time on that, but we'll have a look at it. 4.6 describes requirements for queuing areas. And 4.8 describes requirements for makeup of exhaust air. And this is important. The supply air flow rate must be between 75% and 90% of the exhaust air flow rate. So we're calculating the exhaust air flow rate by using the equations I just talked about. But then you've got to have makeup for that exhaust. You know, we talked about air balance previously. If you've got an exhaust, where is the makeup coming from? And that's got to be considered. So you might have a supply air system, and where you've got a basement car park, you normally will have a supply air system. There'll be a fan and ductwork, which brings air from outside, pushes it into the car park, and then it gets exhausted out. The reason for keeping it below 100% is to create a sort of negative pressure environment in the car park. Because there are other areas around the car park normally, you want to make sure that you're scavenging all the exhaust out of the car park, and the makeup. Like if you've got 100% exhaust air and you've only got 90% supply air, there's 10% air missing. That air will be drawn in from outside or from other areas to create a negative environment in the car park. Okay. So we've been through those notes. Any questions? Any more questions at the moment?
No.
No.
Okay, now I'm going to give you a little tip here. You can do these calculations manually, and for many years that's what we had to do. And obviously you can still do that. And I think it's a good idea to do that to start off with, to do it manually. So by doing it manually, you have to think about what all these factors are and what they mean and put them in. But there is a calculation spreadsheet available. So that's, whoops, what have I done? I just buggered that up, sorry. Calculation spreadsheet number 2 there, which is in your files. If you go to the toolbox and calculation calculators, you'll find a spreadsheet for calculating car park exhaust, and that puts all these, you can select these factors and just plug it all into the calculation. So that just saves you the time of doing it manually. So what I would like you to do when you go through this exercise is just do it manually, and then you can do the spreadsheet as well. Now, I don't know how much spare time you have, and probably not much. But the DALI project, which Philip has suggested and I think he's given this to other guys as an exercise project. It's got 3 basement levels and 2 lower ground levels. So it's a big one, all with car parking spaces. So part of the analysis is to think about, if they are below ground, then they definitely need mechanical exhaust. If part of the car park area is above ground, then you may be able to bring in some, you may be able to use natural ventilation, but I don't believe you can in this case. So those 5 levels will need exhaust and supply. There's a link to the drawings. Has either of you had a look at the drawings?
Yeah.
No?
Not yet.
Okay. Righto, we'll do that in a sec. So first thing I've asked you to do, calculate the mechanical exhaust ventilation rate required for each level and the total exhaust flow rate in accordance with AS 1668 Part 2. So just using the procedure we just talked about, just calculate how much exhaust air you need for each level, and the total is, you just add them up, because you'll have one common exhaust system. It's very rare that you have a number of exhaust systems, but you can do that. But let's just assume we've got one exhaust system in this case. And when you look at the drawings, the architect has made provision for one exhaust duct at the ground level. It shows it coming up through from below. So there's just one exhaust system proposed. And then also calculate the minimum mechanical supply of flow rate required. Well, that's easy because it's between 75 and 90%. So you can call it 90% if you like, but there is the option there. A lot of these things you have to use your discretion, talk to someone who's had experience. What do you think I should use in this case? I know 75 to 90 could be quite a big number. When you've got a basement that goes, down a few levels, I think you'd be wise to use 90%, because what it's relying on is 10% coming from somewhere else. And if you're way down in the bowels of the earth, how's the air going to get there? It's going to be difficult. So work on 10%. That gives you a bit of a negative pressure in that space, which is what we're trying to achieve. So basement 3 is the lowest level, and therefore N2 is 0 for the calculation of C. All levels above B3 must take N2 and D2 into account. Okay, we'll go to the drawings in a minute. The architectural drawings show the number of car parking spaces in each level. So just use that number. If they don't give you that total, you'll have to go through and count them all. And you probably have to count them 2 or 3 times, because you'll think, was that right? And you'll check it again. Sometimes they hide car parks in little spaces that you don't see the first time, you see it the second time. Just use the number that they've nominated. The floor area, to do that, 2.5 times the area. I didn't notice on the drawing that the architect had put the floor area. But if they have, it might be a bit confusing. So you'll need to calculate that manually. And as I said, if you've got enclosures like storerooms or switch rooms, don't include those because the car park ventilation system is not designed to ventilate those areas. This is what I've said there. Now, then the last thing I've said, the drawings nominate an exhaust duct size on the ground floor. Based on your exhaust calculation, I'm just asking you to have a look at that duct size. What's the velocity and friction of the exhaust in that duct? And is the duct size adequate? From what we've talked about with ductwork sizing for a car park exhaust, how does that look? Do you think that's right? I mean, we can talk about that when you've worked that out. And based on information that I gave you previously, you might be able to say, well, I think, let's say 8 meters a second is okay, or maybe 10 meters a second is okay, because it's quite a large duct. It'll be a large airflow, but you find that as ducts get bigger, the friction rate is coming down, but the velocity is going up. So it's really what's the best solution there. And really what we're trying to achieve is the best solution for the lowest cost. Yeah. So a few other items to consider or discuss. We can talk about these perhaps next week. If you have a chance to do this calculation by next week, we can have a look at it. Philip, I don't know whether he's mentioned to you, but I think what he wants to do is for you guys to present this to the team. Okay, at one of your morning meetings or something, you'll show your calculations. Just show the car park, show your calculations and how you went about it, and then you can discuss it, ask any questions. You can do the same with me. So maybe you can do that with me beforehand, and I'll give you a few tips if you need them. So just a few other things to think about as you do this, and you always need to think about when you're doing these calculations is, firstly, can you see how car park makeup air is intended to be delivered to each level? So you're looking at architectural drawings, you're not looking at mechanical drawings. But if there's provision for a car park supply air riser, it should be shown on the drawings. So just have a look for that. Where is the makeup coming from? If you're down in B3, the air's not going to find its way from the ground all the way down to B3 to make up the exhaust. It will to a certain extent, but you really need a supply system going down there. You'll see many other areas on the drawings that require mechanical or natural ventilation. In this case, probably mechanical, but there might be some natural up on the ground floor. Can you identify areas that require ventilation? This is just to think about. Don't go to too much trouble with this. Just get it in your mind, because when you're doing a design, you need to think about these things. Now, I'm just mentioning here as well, I don't know whether you've heard about another method of doing car park ventilation is using CFD, computational fluid dynamics. Sean does quite a bit of this, and he's very good at it. It looks at the airflow patterns and environmental factors to predict the carbon monoxide levels throughout the car park. And the aim of using CFD is to see if we can minimise the amount of mechanical ventilation. Well, basically that's it. In other words, reducing the amount of ductwork, reducing the fan sizes. Maybe we don't even need fans, but we probably will, but we might be able to take out a lot of ductwork, and that's going to make big savings to the project. And there's a few other things I've mentioned at the bottom here. I'll send you this document anyway. We've talked about objectionable and non-objectionable. CO monitoring in the car park that's covered in AS 1668 Part 2. It's where if you're monitoring the concentration of CO, you can control the speed of the fans and slow them down if the CO level is low. We'll talk about that more later. And make up for general exhaust systems around the car park. We need to consider that as well. Let's have a look at the drawings. We've nearly reached time, but I'm quite happy to go a bit longer if you want to. Okay, so here's the drawings. So you can see the car parking spaces here. And there are some areas, like down in this area, for instance, it looks like there's storage cages. So just have a look at those drawings. There's these areas here are lifts, so you can take those areas out. That's a stair. There's a lift over here with a stair, and so on. So I'll just make this a little bit bigger. You can see the basement.
Before you continue, Peter, I just had a question about the calculation of C. So the N2, what exactly is that? So I've got the description here. It says the number of parking spaces situated in other parts, but how would you calculate that? It's
if you're looking at basement 3, N2 is 0. If you're on basement 2, then N2 is the number of cars in basement 3.
Right.
If you're looking at basement 1, then N2 is the number of cars in B2 and B3.
Okay.
So just to think of it in sort of layman's terms, I guess, because the codes tend to make these things a bit difficult to understand. But just try and think back to what are we trying to achieve? We're trying to keep the CO level, control that, so people can actually get out of their cars and walk to the lift without getting poisoned by carbon monoxide. So we're trying to get rid of the carbon monoxide. If you're on B1, all the cars from below B1 are going to pass through B1 before they go out of the building. So they're going to contribute to the CO level in B1. So you've got to consider all of that. But at B3, all the cars are going up from B3. So there's nothing below it.
Yeah.
Okay. Does that make sense?
Yeah, that makes sense.
Yeah, and then D1 I'd have to go back and look at the definition, but it's written down. I think it's quite clear. D1 is the distance a car has to travel from the level that you're thinking about till you get out of that space. And D2 is how far a car coming up from below has to pass through that level. So let's say we're talking about B1 again. If you're coming up from below, how far does a car have to travel from the ramp and around and then go up to the next level? Okay.
You can nominate the half the perimeter of the car park level, right?
You can. Yeah. You can if you just to save you a bit of time of trying to estimate. Like you can look at this and say, well, let's say that right in the middle there will be the average, and do that. But it's easier just to take the perimeter.
Yeah.
But if you're coming from B3, just take the perimeter on B3. But other cars, let's go to B2, for instance. So a car coming up from B3 is coming up, say, up here. You can see my pointer, can you?
Yeah.
It's coming up here, goes across here, and then goes up there, because then it goes up to the next level. So you've got to try and visualise this, that these are ramps, okay? You're coming up, going across, and then up to the next level. And you can see where they've broken it here. That's where the ramps are crossing over, okay? So then, consider that distance as a car coming up from below. That's how far they travel in this level. Yeah. And that would be your D2. So you just have to do those calculations. Look, it can be a bit confusing at first. Just have a go at it, and then we can talk about it. I'd just like you to have a go, see if you, because part of the exercise with a lot of these things is to get an understanding of the standard and the NCC. What's it asking for? If I just give you the equation and we work through it together and you get an answer, you may not get as good an understanding of it as if you have to work through it yourself. I think that's the best way to do it. So then what's this level? So this is B1, but then above B1, you've got a lower ground level, lower ground O2. And again, the key to this that shows you it's underground, or key for me anyway, a quick look at it. Can you see all these piles around the perimeter of the building? That says that's a contiguous wall, which means it's still underground. And you can see the ramps as well. The ramp comes up and then goes around and goes up to the next level. So that's still below ground. Go to the next level, which is called lower ground O1. Now on this level, you have got some residential apartments, but you've still got this contiguous wall around the outside. And this is the ramp coming up from lower ground 2, and then comes up here and goes up again. So it's going up now to ground floor. So that's still below ground. The car park is below ground. There's not many car parks in there, but I suppose there's an option you could look at in the design. Do we treat this as a separate car park? In this case, we're going to treat it as part of the whole car park. So it'll just be added on to the rest. Now, over here, I'll have to make it bigger again so you can see it. I'll go to 75%. See over here, see this note? It says 1400 by 2300 slab opening for a 1300 by 2200 car park exhaust riser to mechanical engineers details. So 1300 by 2200 is what the mechanical design engineer has sized that duct at to pick up all that exhaust. I'm not asking you to look at the duct layout or anything like that. It's just whether that duct is big enough or too big or whatever for the exhaust you calculate. And then I've also said, have a look on the drawings just quickly and see if you can see where the mechanical supply air, makeup air, is going down through the building, because there should be makeup going into each level, supply air into each level. Just as you've got supply air coming in, exhaust air coming out on each level. And then there's the ground floor. So this is, I'll make that smaller again. Again. Okay, you can see the ramp here. So this ramp is coming up from the lower ground. So you've got a line across there. If you stood along that line, you're looking down on the ramp coming up. You understand that?
Yep.
So that's coming up into the outside air. And so this is where you exit the car park, and there's a street out here, Epsom Road. There's a street here, side street, presumably. So this is all above ground. And you can see the contiguous wall is not there anymore because we're on the ground. So how do you feel about that? Happy to have a go at that?
Yeah.
Don't stress over it. Just have a look at it. It's really just to get a feel for how you do these things. And one of the hardest parts for a lot of people, I won't say that applies to everyone, is being able to really understand the drawing. You know, what's actually happening. But if you can understand that these ramps are where the cars are coming up, and then they come up a ramp, go on a level driveway, and then go up another ramp, up to the next level and go round and round. So you need to include that area of ramp in your calculation of area, because the cars are travelling through there. So that's probably about it. If you can have a go. I haven't spoken to Philip about when he wants you to present this, and I guess he hasn't mentioned this to you yet, has he?
No.
So I think it's probably best if you have a go at it, even if you have a go at one floor. But you know, once you've done one, you can keep going and work through it. And we can talk about it next week, because at the moment I'm not scheduled. I was going to continue with ventilation next time, but let's have a crack at this car park exhaust, because this is a relatively difficult topic in ventilation. And if you can master this, well, it's great, because you're going to find you'll be doing this quite a lot in the time to come. Not straight away, but you know, one of the senior engineers will say to you, "Oh, look, I've got this new job. We've got a car park. Can you do the ventilation calcs for me?" Okay, so you need to understand how to go about it, and have a look at that spreadsheet. But I would like you to try and do it manually initially, so that you can work through all of those factors and put the right numbers in, and then we'll talk about it next week. So one of the other things I mentioned was, while you're looking at these drawings, just have a look at other areas that are going to require ventilation. It's probably going to apply mostly as you go up the building to the upper levels, but there'll be other rooms that require ventilation. So just be aware of that, because when you're doing a full design, you have to consider ventilation of everything that needs it. Yeah. All right. Well, I'll let you go now. If you've got any questions, just send me a message if you like, and I'll see if I can help you with it. But give it a crack, and we'll talk about it next week.
All right, sounds good.
All right, sounds good. Thanks, Peter.
Thank you.
Okay, righto. Have a good day.
Have a good one.
Yeah.
Bye bye.
You too.
See you.